Hi, in this video, I wanted to cover with you about complex numbers. And for this, we will use the book Lab. We use this book to cover this topic, complex number, algebra of complex numbers, which is from this book. Okay. So he says a complex number a comma b or a plus jb can be represented graphically by a point whose Cartesian coordinates a and b in a complex plane they will be given by z. So we will call this number in the complex plane a complex number z, which is equal z plus jb. And we also can split these terms, can explain these terms uh, as real and imaginary part in the complex plane, like you are seeing right here. But where this come from? This a equal or cosine b. We know that this is when we we decompose this is on the axis like r times this angle cosine of this angle because this is cosine and that is sine. And when we do the decomposition of this, which we can call a vector r in the Cartesian coordinate, we can decompose this vector on the axis, multiplying the the angle theta by this vector, and is the same for b, which is on the imaginary axis. So right here, sine, if you multiply the vector r by the sine of theta, we will get this part right here, which is the vector decomposed. But why the complex number z is equal a times a plus j times b? Let's see this. If you draw the trigonometric cycle, this way, and this is the axis, the x-axis, but this is imaginary, and this is real part, and we not use actually y and x. And if we have a vector which is outside of this Cartesian axis, like or like we were seeing this vector, we can decompose in a axis component. So this component is for the real part, which we are calling A, and this is cosine. And if we decompose this vector in terms of sine, we just have to multiply theta, and this is B for the imaginary. So for the B, we have the imaginary. For the real, we have A. So this is what we are doing. Is R, which is the vector, times the cosine of theta, and for B, and those are components of the vector R, which we are decomposing uh, based on this angle, R times sine of theta. And an important detail is this part is positive, this is positive, is negative. So for the cosine, we will have and for the sine of theta will be minus sine of theta, because of this this region of the trigonometric circle. So as this is the imaginary part and this is real part, we're going to have the following for the Euler equation. Euler exponential of g times theta is equal cosine of theta plus j times sine, and if we multiply both sides of this equation, and remember we are trying to figure out why we got this complex number in this way. multiply both sides of the equation for a constant number, like we can multiply by a, right here too, both sides. So we got in and now to simplifying the things, we say this is a and that is b, j. And Euler is this formula is used to convert numbers in the um, Cartesian coordinates for the polar coordinates. This way is polar and this way is Cartesian. So that is a Cartesian polar coordinate. And that is equal a cosine theta or b sine theta. Sorry, a sine theta. And this is for polar Cartesian, polar coordinate, sorry. And this is Cartesian. And now you know why a complex number z is represented this way. Okay? For now, I think uh, that is enough. In the next video, we will write sine and cosine in the exponential forms. Okay, that's it. Thank you for watching.